iniciar la sesión 3. Good afternoon. We are going to start session 3, Deep Learning and Neural Networks. The next exposition is Local Context Attention Network for Diabetic Retinopathy Severity Classification by Dora Alvarado Carrillo, Emanuel Ovalle Magallanes, y Oscar Dalmau Cedeño. You have 15 minutes for your presentation and 5 minutes for questions.
Hi, welcome everyone. I am Dora Alvarado, and today I will be presenting our work, LCAM-NET, a local context attention network for diabetic retinopathy severity classification. This is a collaboration with Emanuel Ovalle from Universidad de La Salle Bajío and Oscar Dalmau from CIMAN. So, in the last decade, deep learning techniques have completely changed the field of image analysis, and in particular, they have been powerful techniques for diagnosing conditions in which we have these complex visual representations of data. And this is all great. We here in this figure have examples of some different modalities of image or medical images that can be diagnosed using deep learning, but they also have a problem, which is the lack of interpretability or the lack of explainability. So for the particular case of diabetic retinopathy severity classification, here I am trying to put into perspective this problem. So a deep learning model would receive this kind of input data, which is a fundus image, a photograph of the interior surface of the eye. And the expected output would be a classification, a class label and a probability score. These two data would help us to identify the severity of the condition, but they wouldn't provide any other explanation on how the model came out with this decision. So why is this a problem? Because for clinicians and patients, it's important to have an understanding on the underlying decision-making process in order to trust the system and in order to take some important decisions about their healthcare. So what we would like is to have these kind of models in which we can include some methods to enhance explainability and try to provide more information about the predictions. So for example, here we have a heat map where we are highlighting regions of the input data that were relevant to take this decision, to make this prediction. And another example could be to have a caption or a description about the abnormalities that we found in this input data. So here in this work, what we are trying to do is to provide better answers for these two questions about why and how a prediction is made in order to increase the trust on the diagnosis systems. And in this specific case, what we are doing is proposing an attention mechanism to include on a convolutional neural network in order to improve these kind of visual explanations, because we not only want to have this kind of heat maps that we are highlighting important or relevant regions. We also want that these regions match the areas of these input data that are lesions or abnormalities. So this is what we are working here. So let me introduce the local context attention module, or LCAM. This module is inspired in these pre-processing techniques that we are using when using traditional computer vision algorithms. So what we are trying to do is to extend these techniques into a convolutional neural network And we are doing this by using intermediate feature maps as input of the attention mechanism. And also we are using this special constraint convolutional layer. This layer differs from the original convolutional layer, in which we have two restrictions or two constraints of non-negativity and a normalization of the weights of the convolutional layer. And these parameters of the layer are represented here in this variable. So here I am simplifying the process of the attention mechanism, but basically we have these main calculations. Firstly, we need to compute this adaptive local means map by applying this constraint convolutional layer over the input data. And next, we calculate this local variances map by taking this squared input and applying the same convolutional layer than before. I mean the same filters and the same parameters than the previous step, and subtracting the square local means map. And finally, once we have these two calculations, we use them for applying a normalization, a local normalization step here. So what we are trying to do, we apply this normalization by subtracting the local means map and dividing by the local variances map. So what we are trying to do with this process of local normalization is to bring out regions of the image or the feature map that might have these different values from their local surroundings. For example, in the case of a fundus image, we have these lesions that have different intensity values with respect to the normal retinal tissue. So that's what we aim to do with this local normalization process, with the difference that the parameters or the weights that we are applying to this normalization are learnable. They are the parameters of this convolutional layer. So let me show you some experimental results that we did with this attention mechanism. So we did this ablation study to try to understand the impact of adding this attention mechanism into different well-known architectures for the classification problem. So we are using these well-known models, Inception, ResNet, DenseNet, and EfficientNet. And we are trying out what happens when we add this attention mechanism. So here we have the results for baseline models, and also the results when we add this attention mechanism. We are also trying out different sizes for the receptive fields in order to understand the impact of this change in the configuration. So what the results show is that for most cases, when we make this addition of the attention mechanism, there is a positive impact over the performance metrics. For example, let's look at the kappa score. In the case of the Inception version 3, for the baseline architecture, we have a score of 47% for the kappa score. And when we include this attention mechanism that we are proposing, this value increases up to 71%. And similarly, for the accuracy score, we also observe this gain or this improvement when we add this attention mechanism. For example, in the case of ResNet, we obtain with the baseline configuration an accuracy of 55%. But when we include this attention mechanism, it raises up to 64%. And another observation is in the size of the receptive field. For most cases, we observe that the best result for across these different architectures, it's obtained when using this configuration of 5 by 5 units for the receptive field. From the previous study, we took the best configurations and compared with several state-of-the-art methods, including some of the baselines from the previous study. And what we see here is that the addition of the attention mechanism, the LCAM, improves and has a competitive performance comparing with several state-of-the-art methods. For example, in the case of the configuration where we are using the efficient net with the LCAM with a size for the receptive field of 5 by 5, we obtain the best kappa score, which is 69%. But in the beginning, I said that what I wanted was to improve this explainability that we have with the models. So we also studied this effect in the different architectures that we tested. Here we have a GradCam visualization for trying to understand the most important or the most relevant areas of the input data that are taken into account when doing the classification. So here we have some examples of original images that we have as input for the model. And here we have the results of the GradCam for the baseline architecture of DenseNet. And the last column corresponds to the results where we have this modified architecture where we are adding this attention mechanism. And what we see here is that for most cases, when we add this attention mechanism, we are improving the areas where the model focuses on, because they tend to identify relevant areas corresponding to the lesions from the original image. For example, lipid deposits or blood deposits that are identified here in the original images. So here we presented a new deep learning module based on local special attention, LCAM. And this mechanism that we presented was designed to recognize salient elements, and it's trying to implicitly guide a classification model towards variations and irregularities in fundus images. And the inclusion of this LCAM into a convolutional neural architecture resulted in a positive impact in performance metrics and a classification indirectly based on lesions and abnormalities in the fundus image. Also, we show with the ablation study that these LCAM-based models have demonstrated competitiveness and computational efficiency, and they also require a small input and simple processing. Most of the models that we see in the literature in many papers, they have to apply many steps in the pre-processing step. And here we are simplifying this, and we are not using any special pre-processing method. So this issue would speed up the training and the inference steps. Thank you.
Thank you for your presentation. How do you select the slide in which you introduce your attention model?
In the case of retinal images, they do not have a volume as in MRI or other kind of medical images. So what we have is an unique image of the interior of the surface of the eye. So I do not need to select a slide. I don't know if that answers
but
the
in the
question.
structure of your convolutional neural network, do you select any part of this deep structure
Okay.
in which you include the module?
You mean in which part of my model do I include the attention
Exactly,
mechanism?
Yeah.
It depends on the architecture. We study different papers in which they add an attention mechanism for spatial attention, and we use them as guide to include our method. So we didn't experiment with the part of the network or the deep in which I include the mechanism, but it would be interesting also study this part.
It's not a recipe to use to guide the.
No, it depends on the architecture mostly.
Okay. Thank you.
Thank you.
Hi. Where is the attention mechanism on your formulation? Because I know the attention mechanism from Transformers, and this is the first time I see. That's my question. Where is the attention mechanism?
Where is in the network, you mean?
Or in your formulation you present?
Well, this is the design. I think that for vision transformers, you apply the attention mechanism for sections of the input image, right? In this case, you take the whole input feature map and you apply these operations to all the data from the input. So you don't have to take sections of it. And the part specifically where this is applied, it depends on the architecture.
Okay.
For most cases, well, it depends, but it might be, for example, in the case of the inception B3, where we apply different sizes of convolutions, you could apply the attention mechanism after that part, but it depends on the architecture. So,
thank you.
Why did you decide to use this dataset?
you mean the IDRI?
Hydrate.
I didn't mention it because it's very few minutes for the talk, but I'm going to go back here. We are using this IDRI dataset mostly because it has a well-defined partition for training and test. So this is easier when we are comparing with many state-of-the-art methods here, because they also use this data set, so we can have this study. Another feature of the IDRI data set is that it has around 500 images for training and testing. I think are around 400 for the training and 100 for testing, so it's easier this part.
Okay, thank you.
Thank you very much. We continue with our next talk. Is Andrés Cureño Ramirez here? The next talk is image classification with recurrent spiking neural networks.
Hi, good afternoon. My name is Andres, and I came from Simvestav. Want to present image classification with recurrent spiking neural networks. The outline, we are going to see introduction, some kind of the spiking neural networks, experiments and results, conclusions, and some references. As part of the introduction, neuromorphic computing will be important in the future, and it can be defined as a non-von Neumann computer, so it's another kind of architectures. These are inspired by the brains and are composed by neurons and synapses. As the spiking neural network is going to be the primary unit of this kind of architectures, and partially in our brain, it's supposed to be a SNN with about 100 billion neurons that just consumes 20 watts. It's something important because a GPU, it's around 150 watts. And we cannot simulate that kind of neurons. But nowadays, to perform classification tasks, it's something that is really easy with the deep learning techniques, but for neuromorphic approaches, it's a really big problem. The spiking neural networks, the first thing is that they do not use nonlinear function as sigmoid, tan, I10, or ReLU. And they are described as differential equations, so they are time dependent. That's a really important thing because when we are going to train this network, these neurons, we are going to take in account the time. Let's do this. We implement this in SNRTorch and with Python. We can see that we have the next voltage of the membrane. Also beta, that is the membrane flotation decay. Input current, this is the reset mechanism. If we pass some threshold of this kind of networks, we're going to present at the next step a spike. If we do not pass that threshold, we are not going to present a spike. But if we present a spike, we are going to reset the neuron. So the input is going to have spikes. But also we can have a recurrent neural network, and we are going, in the equation 2 and the equation 3, we only add this B. That is the recurring weights. But it's also the same. We have the spike or not the spike in time. The main problem is because we have pulses, so maybe in all the training, not all the neurons are going to be activated. So that's a big problem because we cannot differentiate that, because maybe in all the training that maybe one neuron is going to be the same, so there is no change. So all the backpropagation methods didn't work that well in this case, but we can add a surrogate gradient to this. Instead of the equation number 4, we can approximate this with this kind of network, of this kind of equation. So the derivative is going to be like this. There are a lot of works how to train this kind of networks, but this is the equation that we use to train this. So the experiments, we create our own dataset with 8 classes and 200 different samples for each class, and each has 64 by 64 pixels. So in total we have 1,600 images like this, and an augmented dataset that has the same figures, but they are scaled and also rotated. So, but this dataset is not going to be to train our network. So they are going to be like a valid test. So the preprocessing for this, each image was cropped to a new image size of 53 by 53 because the margins, there's no information for us because it's just white. And each image was binarized using a threshold of 127. And the pixel values were normalized between 0 and 1 and to simulate a spike of the image. And this image were flattened to a vector of 2,809. That is going to be the input of our network. And we divide the first data set into a training of the 80% and 20 to the remaining data, just for the testing. So we have a training, a testing, and a validating data set. So the architecture to propose this kind of networks was taken from the work number 1. We take a recurrent spiking network with the recurrent weights. This is the activation function that is going to be the pulse. If the new voltage passes the voltage threshold, we are going to generate a spike, and only the spike is going to pass to the next layer. This is like a quickly explanation how this works. We have the input image. The input image is just zeros and ones. This is the input, the weights, and then the recurrent weights is going to produce only ones and zeros instead of the sigmoid or the tan 18 or the ReLU. This creates a lot of sparsity, and the output layer is going to generate only ones or zeros that are at the pulses, or maybe it could be a real number because it's the output layer. So then we have to summarize all the time because it's a differential equation, so we have to take into account the time. And then we have to summarize all these steps. We can use the output voltage of this network to make regression, but we are going to present some results to make classification only. So we train this. We train this in using a computer with these specifications: GPU 4060, RAM 8 gigabytes. We only use one seed. The input is the 2089,809. The recurrency of the reservoir of the recurrent is 50. And the output is 8 because of the 8 classes. The outputs, the values for the decay, 0.9, and the voltage threshold is 1. We don't use any bias. And the epochs 30, the batch size 80, numbers of steps, the T is 10, loss function close entropy, and the optimizer is the Adam. For the training, the testing sets, we have a really good confusion matrix. If you can see, it's all in the diagonal for both, using also the output spikes or the output potential. But there's a problem. If we use the augmented data set that has the same figures but also translate and rotate it, we can see that the network didn't generalize all these features, even that they are the same. Some works said that it's better to use the output potential or the count of the spikes. But if we see, there's not a lot of difference between using the output potential or the count of the spikes. And it's also easier to use only the count of the spikes because it's just 0 and 1. We don't have to approximate anything with just zeros and ones. Just for conclusions, we create our own dataset test to compare different methods to do classifications with the RSNN. For future work, we would like to explore the search of the best architecture to solve classification and regression tasks, and how to tuning these hyperparameters of the network. Because as you can see, we have to control how quickly it's going to present the pulses, because it can increase the frequency of the pulses. Also, where is going to be the threshold, how long is going to be the reservoir of the recurrency. One other important thing that there's still no consensus on how the image should be introduced to this kind of networks. Some of the papers that I read mention that we can pass that image to a neuromorphic dataset. I don't think that it's a good idea because the image is a static thing, and that time is going to make it like a video. Another one just introduced this image as zeros and one. Another person said that we have to pass this image as grayscale and then make this as a pulse. We leave as an open question in which kind of task this kind of networks can achieve better results than the current state of the art machine learning methods, because this problem was easily solved using a support vector machine and the human moment. So this kind of networks, it seems to be better to process abstract data, like, I don't know how to say, to smell things like we do. If we are, maybe we're in a restaurant, we can perceive as humans a lot of smells of the things, but that is a difficult task for a computer to separate that kind of things. And another, just to listen as someone between a crowd. That is a really complicated task for a computer. And that's all. Thank you for attention.
Thank you, Andres. We have time for questions. Please.
Thank you for your presentation. I'm curious on two regards with your investigation. First, how many neurons or spiking neurons did you apply to your model? And also, as far as I understood, the encoding phase that it's needed in order to change from an image into a spike train, which is necessary for spiking neural networks, it's only by a threshold. But there's several methods. Have you tried any other of these methods?
Well, for the first question, we just, as model, we just proved the LIF, this one, as model, just one, because there are a lot of models. Okay. The main problem that maybe I am working in another model that has three differential equations, and just for one output, we wait 2 days to produce one spike train, because you have to solve all the equation and to produce a spike train that you can use. And now, what was the? Yes, we only use this binary threshold because, as I mentioned, there is still no consensus how to introduce this image to the network. If you look in the internet, you can find some tutorials, and they introduce as a grayscale, but normalized. Other introduce just the grayscale without a normalization. Other pass the image to a neuromorphic dataset that I think is, you are adding a step to an image that don't need to do that because it's an image. Maybe if it was a video that you have frames, could be a better thing. And I just use the threshold because it's just zeros and ones. That I think is a pulse. Exists or don't exist. But as I mentioned, there is another one that you take this grayscale and you multiply by a probability. Maybe if you have the grayscale and it's 0.2, normalize the image. In that pixel, you're going to have just 2 pulses in that train. Okay. But there are a lot of methods, as you mentioned.
Yeah. Also, just one suggestion. There's a algorithm that has been released, I think, for 3 years now. It's called backpropagation through time, which is specialized for spiking neural networks. I don't know if you try to implement it, because by using the surrogate kind of way to training these neurons, they tend to overfit, which is, I think, what you are encountering here.
Yes, well, maybe I will be really quick there, but as when I started to investigate this, I thought that that was an open problem, but there are a lot of things that are solving, as you mentioned. And in the SN torch, there are a lot of the back propagation through time is solved.
Yep.
Just you can change the derivative as you want to,
Yep.
wherever you want.
Okay. Thank you.
Another question for Andres? No? Okay. Well, thank you very much, Andres. Here's your diploma. Thank you. We have Jose David Velasco here. Okay. Our next talk is reducing parameters by neuroevolution in convolutional neural networks for steering angle estimation by José David Velasco Muñoz, Héctor Gabriel Acosta Mesa, and Efraín Mesura. José David, you.
Thank you. Hello, good afternoon, everyone. I am José David Velasco Muñoz. I am a student of postgrad Artificial Intelligence in the Instituto de Investigaciones de Inteligencia Artificial, in here, the house. And I present the reducing parameters by neuroevolutions in convolutional neural networks for steady angles. Okay, a brief overview in this project and agenda, a little introduction about the autonomous vehicles, the different application of steady angles in this project, and relate words with these projects, methodology proposed, experiment results, and conclusion. Well, it's important the developments in autonomous vehicle, the different applications, for example, in direction or Internet of the Things, the different connections about in autonomous vehicles. The development of convolution network has a significant impact in autonomous vehicles. It's the model more popular in this application for this. And the reason of the challenge of optimization fundamental aspect when network could open the new possibilities. There are it's necessary to design the specific networks for specific applications in autonomous vehicles. In this project, this applicate about the prediction estimations, the steady angles. When I drive in a car, you have put the steering wheels, put the different direction the vehicles depending the paths or the lines when you drive in the car. Well, in related words, we can find the different designs in convolution networks for steady angles, designing specific for expert the convolution networks, and transfer learning the using these networks, designing in different applications, and optimize the convolution networks by evolutionary algorithms in this project, in these applications, and compactations convolution network techniques, the pruning or quantification. Well, there are different architectures for layers, the number of layers, and the full connect, and the using data set the real images in the paths. there are the different parameters that they're using in architecture about the use in BGG16 or RISNet or convolution networks for design for expert. There are the millions parameters or the different types parameters. Well, in methodology, well, this is methodology in this project. I use the data set. The data set, I use 1,000 images, and these images for the labeled the angles for the depending the setting wells when you count the estimations the frame to frame in images. There are different types the angles when you drive in a cart. For example, in this case, when you drive in a line, it's a little estimations. When you turn right, for example, you need more estimation or more angles in the studied wells. Well, is the first step, and the second step is recite these images, enable the artificial intelligence system to rapid analysis the visual data, and is facilitate in neuroevolution process. The neuroevolution process is a genetic algorithm inspired the evolutionary the process, but in this case in neuroevolutions you need the network for populations, and the populations, the selections, the parents, the crossovers, and the mutations, the different generations in this part. You need the different parameters, the population size, the generations, and the crossover percents, crossover mutations, or depending in the process. In neuroevolution, you need initialization parameters and hyperparameters for create the initial convolution networks for the process. And in neuroevolution, you need the fitness function for the quality estimations, evaluate this network in this process. In this case, they use MAPE. MAPE is a function, a loss function for a quality predictions in regression networks. Well, what is the parameters in convolution networks? Is the filters, is the filters, number the filters in layers, the filter signs, the dimension of filters, what is the size, the filters, the pooling layers, if the average or off or other types, the pool signs. And it's important the full connect, the number networks and the number connections they using in parameters in convolution networks. Well, there are this architecture for comparate the networks by neuroevolutions. In this case, I use this, this is networks with this architecture, the pilot net. This is very popular in convolution networks for steady angles, and ResNet, the use in literature, BG16, and this architecture optimized by PCO. These architectures and the other architectures created by neuroevolutions, I use the statistical at convolution networks, the comparate process. You need the test Kolo-Smirnov. You need to see the data normal distributions and the Kolo-Wallis if the difference, the medians in the groups, and the man's comparate and experiment and results. I have these experiments, the 10 runnings in the MAPE. The lower MAPE, it's a good predictions when this MAPE. and the plotting a map in the process generations for the genetic algorithms. And the number of parameters, oscillation, the parameters, but the number of parameters is lower the parameters when they finish the process. While the mean square error after the generations in the process, the genetic algorithm. Well, I obtained this architecture. The name is DeepGA steady tangles. The name, the algorithm is DeepGA for steady tangles. And this the architecture, 3 layers, the convolution networks, and 2 layers for full connect, which is the number, the networks, and the final, the layer regressions. This architecture compared with the other architectures, with the when training, when 10,000 images, with these hyperparameters, yes, hyperparameters they using for training these networks with these architectures. And the results, the comparative in convolution network in parameters, I see the few words, the convolution networks with the 35,000 parameters with different parameters is the median or the difference in the proposing literature convolution network. Well, in this graphic, I put the performance, the different architecture, the mean square error, and the log parameters. There are much difference in parameters and the log parameters. The graphic, I see these are a good performance with the different other architectures. PyLoNet is bad, but this convolution network, but the number parameters it's allowed with the difference the other architecture. Well, in experiment, the statistical conduce the team runnings the convolution networks for training MCA of 15 epoch, indicate the node distribution normals, and in the conclusion in this process experiments, it can say that the DeepGA, the architecture obtains, it's similar performance with other architectures with the more parameters, depending having a smaller number of parameters. Well, in conclusions, the finding demonstrate the genetic algorithms parameters have successfully converge, showcasting. The neuroevolution is an approach for create the architectures and the different the behaviors. This is the reference about the convolution networks. And thanks you for attention.
Thank you for your presentation, Jose David. We have time for questions.
Hi. What was the size for your population?
Population? Yes.
And how much did that increase the time of the training?
Yes, the population is 20 individuals in the process of neuroevolution. Yes.
And how does that increase the time of the training?
Yes, yes. If you put the more population or more individuals, they create more the times for the training the networks. Yes.
And what was the stopping criteria to all the
oscillation, the
all the
yes, yes. Yes, oscillation, the parameters for
how the it's a genetic algorithm, no?
why the oscillation of different parameters?
No, how do you know that you reach the best you can?
You can reach.
Uh-huh.
Oh well. Well, I don't understand this question, but
¿Cómo seleccionaste la mejor red?
el accuracy.
La mejor red.
How just
Okay. Excuse me. But what's this? Yes, I select the best res, but the number parameters and the mappe. When the mappe is a low, for example, the 90% is a good predictions in these values. Yes, I see the mappe for the select the architecture.
Well,
12. Yes, this reference.
you are
Yes, I using this. Okay. I use the network because it's a competitive in when the difference other option, other techniques, the compactations in the create the networks. Yes, I guess the parameters is more easy to select in the genetic algorithms for create the networks.
For the next talk, I think we're going to do a video conference. We are going to wait 5 or 6 minutes until 4 p.m. for these guys connect to the video conference. We are ahead in the program, so we can wait 5 minutes. Thank you. Hello, is Carlos Orozco? Okay, we are a bit ahead in the program. Are you ready to start your presentation?
yes, yeah.
Okay, just let me do the presentation here to the public. The next talk is Learnable Gabor Filters in Convolutional Neural Networks, Avoiding Filter Degeneration via Early Stopping Based on Similarity Metrics by Carlos Orozco Solís, Alfonso Rojas Domínguez, Héctor Puga, Manuel Ornella Rodriguez, Martín Carpio, and Valentín Calzada. Well, Carlos, if you are ready, we can start. Okay, please. You have 15 minutes for your presentation. Okay.
Good afternoon. My name is Carlos Fernando Solis. Today I will present my research titled Learnable Spatial Filter in CNNs, Transforming Interface Layers for Enhanced Filter Extraction. Research explores how we can use Gabor filters in the initial layers of convolutional neural network, CNNs, to improve filter extraction. Here we can see the content of this presentation. As a summary of my research, with the evolution of deep learning, we have moved from a stage of manual filter design to one where filters are automatically learning deep networks. Double filters have proven to be extremely effective in detecting edges and texture in images, especially in early layers of CNNs. However, we observe that these filters tend to converge to a suboptimal configuration in degrade over time. My proposal includes a strategy to timely detect this degradation and that training accordingly. Convolution neural networks, or CNNs, are a type of deep network architecture that has revolutionized the field of image processing. Unlike traditional filter extraction techniques, where filters were manually designed, CNNs automatically learn each filter through their layer structure. Recent research has shown that spatial filters, such as Gabor filter when used in early layers, can capture edges, texture, and other fundamental characteristics on images. Despite the advantage of Gabor filter in CNNs, the lack of exhaustive analysis of their parameters has limited their understanding and performance. We have now found studies analyze the convergence of Gabor filter. In my work, I propose using similarity metrics to monitor the behavior of filter parameters. And we developed an architecture called GaborNet2. In this network, its first convolution layer is replaced with a Gabor layer, which has 12 filters, reducing the number of parameters that need to be learned. The Gabor layer uses filter defined with the following mathematical equation. First equation consists in two main parts. The Gaussian part of blue line, which controls the amplitude spatial distribution. The sinusoidal part of red line, which introduces the necessary oscillation to detect specific frequencies in the image. To better understand this function, it is essential to consider the transformation on an x and y coordinates. Second and third equation. This equation allows for the rotation of the image space coordinates based on the angle theta. Additionally, the first equation can be expressed in its real and imaginary parts. In this work, only the real part was used for the equation, where x and y denote the pixel position in the spatial domain, w represents the central angular frequency of a sinusoidal plane, theta indicates the orientation of the filter, c controls the plane of the sinusoidal oscillation with the Gabor filter, and sigma represents the standard deviation of the Gaussian. The experimental setup. In our experiments, we use the MINIS dataset, a database containing 18 digits. This set consists of 60,000 training images and rate of 0.001 in a batch size of 256 images. Additionally, we implement cross-validation with 50 repetitions if the chosen optimization algorithm was Adam, known for its efficient in network convergence and tuning. The initialization of the parameters of the Gabor layer is based on the method described in the Meshgini 2012 article. Frequency W initialized according to the five equation, orientation of data initialized using the sixth equation, key phase XC initialized with a uniform distribution between 0 and pi, seven equation. If standard deviation approximate with the height equation. Two types of initialization were evaluated, independent and trained. Independent initialization means that the 12 filters of the Gabor layer are randomly initialized with a different seed for each run or repetition. Same initialization means that each filter in the Gabor layer was initialized using the same random seed each time. Note, the two traditional convolution layers remain frozen during training, preserving the initial values across all convolution filters to give more relevance to the Gabor layer. Experimental results. In the following graphs, we present only the results corresponding to the same initialization. This is because the experiment with independent initialization yielded qualitatively similar results and led to equivalent conclusions. The left graph represents the evolution of the loss during training and validation. The red line indicates the loss in the training set, while the blue line shows the loss in the validation set. Right graph shows the evolution on accuracy through training and validation. These loss and accuracy graphs do not reveal unusually finding in the behavior of the Gabor layer parameters. The convergence of the parameter in the Gabor layer we tested by conducting 50 runs of repetition, training Gabor-Net 2 and recording the value of each filter parameter per iteration to observe the average behavior of the parameter across the entire set of 12 filters during training. This figure shows the results of the parametric convergence of the 12 filters using the equally filtered initialization. For better interpretation, the mean value we center at 0 in the difference in the mean value between iteration per filter was plotted. This processing effectively shows the shape of each parameter regardless of its actual value. This is displayed at the shaded line in the figure. Additionally, the standard deviation is present as shaded regions around the mean value. I can be observed that both the sheet of the chain in dispersion are insignificant. The lack of convergence in the Gabor filters led us to examine its filter in the Gabor layer as they train, which allowed us to discover that after a few epochs of training, the filter exhibit gradual degradation as illustrated in the figure. The final step in our methodology is to calculate similarity metrics between the filters in the Gabor layer, following the assumption that some of these metrics could be used to detect the point at which filter degradation began, and thus identify a good time to stop the training process early. Hamming distance. The percentage of elements, coordinates, or dimensions that differ between U and V, or Hamming equation, where the function represents the number of occurrences where the condition in the argument is satisfied, while entropy of the grayscale image, in this case, each Gabor filter is a measure of randomness that can be used to characterize the image. Entropy equation, where P contains the histogram counts for the input image, which were treated as 8-bit the grayscale image, thus producing 256 histograms. As can be observed, these two metrics and this experiment allow the identification of the turning point around epoch 16. Correlation based on distance. One minus the sample correlation between points, the sequence of values and x and y. With the metrics, the degradation behavior is observed much more clearly, where this point has been marked in blank. This point, in fact, it prevents significant filter degradation. During our analysis, not only was there a lack convergence in the Gabor filter parameters, but also a gradual degradation of the filters after a certain point in the training process. We speculate that degradation of the Gabor filters occurs because the fully connected layers might have learned many useful filters to allow the network's proper performance, thus facing overtraining. We have described our methodology and process solution based on calculating a correlation-based distance metric between the Gabor filters to identify the point at which training in the Gabor layer can be held to prevent filter degradation. Here are the main references used for this work. I appreciate the attention given and have a nice afternoon to everyone.
Thank you, Carlos Orozco. We have time for some questions. Have questions? Carlos Orozco. Oh, I have a question, Carlos. What is the motivation of your research? Why do you want to learn Gabor filters in convolutional neural networks? Can you explain, please?
Oh, okay. My motivation is I not have studies. ¿Cómo explicar? No existe exhaustive analysis de parameters de Gabor filters y has limit to understand performance using the Gabor filters and CNNs.
But do you have some application in mind or not? Just theoretical interest?
Sorry, no. Eso no escucho muy bien la última pregunta.
Do you want to apply it for some application, motion analysis, texture analysis, or something like that, or not? Thank you very much, Carlos Orozco. Thank you very much. Okay. We have finished session 3 and we have time for coffee break and we'll come back 40 minutes after 4. Thank you. ¿Sabes quién va a moderar la siguiente sesión? ¿Quién va a moderar la siguiente? ¿Tú? Ah, ok. Y pueden indicar